Hey guys, welcome to the Chemistry Grade 11 Masterclass. The information that you need for your exam should be right within this book that I've made, but since you don't have the book, I'm just going to read it out. It's mainly for myself so I can study better. I bet this is never going to see the day of light, but if it does, make sure to like and subscribe to whatever this is being posted on YouTube, Instagram, whatever, I don't care. Alright, let's start. Starting off, the atom. The atom is made of subatomic particles, protons, neutrons, and electrons. Protons are positively charged particles. Neutrons are uncharged particles, and electrons are negatively charged particles. Electrons occupy shells or orbits around the nucleus where the protons and neutrons are located. Protons and neutrons both weigh 1 AMU, which stands for atomic mass unit, while electrons are 0.000, a bunch of zeros, and then a 5, AMU, so it's pretty much negligible. Standard atomic notation, so there will be the element symbol. At the top left, there will be a number. That number indicates the mass number. And at the bottom left, there will be another number, which indicates the atomic number. The atomic number is the amount of protons in an atom's nucleus. The atomic number and the number of protons determines the identity of an atom. The mass number is the sum of all protons and neutrons in the nucleus, not including electrons. Since the mass number is protons plus neutrons, we can determine that the number of neutrons is the mass number minus protons. Since all atoms have zero net charge, positive charges equal negative charges, and therefore the number of electrons is equal to the number of protons in an atom. Isotopic notation. This is basically just the element symbol, a dash, and then the mass number. So X dash A, where A is the mass number and X is the element symbol. So for example, phosphorus would be P-31 or just P31. Bohr diagrams and Lewis dot diagrams. You really can't explain these. Bohr diagrams, in the middle has a nucleus where you should indicate the number of protons and neutrons, and then you will draw the encircling electron orbits. The first ring always holds 2 electrons and the rest hold 8 electrons. For the Lewis dot diagram, you're just going to draw the element symbol and then dots indicating the number of valence electrons surrounding the element. Ions. An ion is an atom that has lost or gained electron and is now charged. A cation, or a cation, is positively charged metals. You can remember that because cation is positively charged. Meow. And anions are negatively charged ions. So cations are usually formed by metals and anions are usually formed by nonmetals. The Bohr diagram and Lewis dot diagrams for ions are a little bit different. You do the same thing as you did before for the Bohr diagram, nucleus with the number of protons and neutrons in the middle, and this time you're going to do your electron orbits, and each orbit is going to be full. And at the end, you're going to bracket around the Bohr diagram and put a number outside indicating how many electrons have been lost or gained. So for example, phosphorus, there would be a bracket around the Bohr diagram indicating, there would be a bracket around the diagram with a 3 negative that indicates 3 electrons were gained. And for a Lewis dot diagram, it's basically the same thing. You're either going to have an empty or an element symbol not surrounded by electrons or surrounded by all 8 electrons. And then you're going to do the same thing, bracket and number outside indicating how many electrons are gained or lost. Neutrons are important. They provide space between protons to minimize repulsion and stabilize the nucleus. They also attract the protons to stabilize the nucleus more. This leads into isotopes. Isotopes are a form of an element with the same number of protons and the same atomic number, but a different number of neutrons, meaning a different atomic mass. The repulsive electrostatic force is the repulsive force between protons, and the strong nuclear force is the attractive force between neutrons and protons that keeps them bounded together. This is 40 times stronger than electrostatic repulsion. Radioisotopes are atoms with unstable nuclei, typically nuclei with 80 plus protons that emit subatomic particles to stabilize themselves. For example, a proton, a neutron, or an electron. Now, average atomic mass. Average atomic mass takes into consideration the mass and abundance of isotopes in nature. So, for example, how much one isotope appears of phosphorus and how much the other isotope of phosphorus appears in nature affects the average atomic mass of phosphorus. So the formula for average atomic mass is on your worksheet, but it is also the mass of the first isotope multiplied by the abundance of the first isotope plus the mass of the second isotope multiplied by the abundance of the second isotope, etc., etc. Continue until you're done with your isotopes. The mass of the isotopes is in atomic mass units, AMU, and the abundance of the isotopes is percentages. And by the way, 100% equals 100 divided by 100, so to get percentage, just divide by 100 or multiply, whatever, same thing. If you have two abundances that you don't know, let X represent one abundance, so that 1 minus X is the abundance of the other isotopes. So, for example, you have the average atomic mass, which is 63.54. And you need the abundance of isotope number 1, which is 62.93 AMU, and isotope number 2, which is 64.93 AMU. You can make X represent the abundance of 62.93, which means that the other abundance will be 1 minus X. So 62.93 times X plus 64.93 times 1 minus X. All right, page 2. Now we are going to go onto nomenclature. Really not easy to put this into words, but you get it. So for the eight compounds, like bromate, sulfate, carbonate, blah 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 blah. When one ends with bromate, when one ends with 8, it means it has the regular amount of oxygens. When it has 1 less oxygen, you end it with ite. When it has 2 less oxygens, you start it with hypo and end with ite. And when it has 1 extra oxygen, you add per at the start and 8 at the end. So bromate is just regular bromate, regular amount of oxygens. Bromite is 1 less oxygen. Hypobromite is 2 less oxygens. And perbromate is BrO4, which is 1 extra oxygen. And also, don't forget old names like, plumbic, ferric. I mean, I have that memorized. I don't know if whoever listening does, but remember that. Oh, yeah. For the old stuff, if it ends with ic, it means it has the larger charge. And if it ends with us, like OUS, it has the lesser charge. So ferric is +3. Yeah, +3 iron. And ferrous is +2 iron. Now for oxyacids. There are many different ways. There are many different names of acids that all sound really simple or similar. So, for example, sulfuric acid, sulfurous acid, and persulfic acid. Now, what's the difference between all of these? Well, I'm going to go through that. Sulfuric acid is when the acid is combined with what are the name of these? The compounds with the oxygens at the end, the oxy things. It's H2SO4, indicating that it is an acid of sulfate. Now for sulfurous acid, it's basically the same thing, but since it ends with OUS, it means it has 1 less oxygen, so therefore it's H2SO3. And persulfuric acid is H2SO5 because we saw before, per is for 1 extra oxygen. And by the way, for oxyacids, ic replaces 8 and us replaces ite. You probably don't know what that means, but I really do not care. So, binary acids are completely different to these oxyacids. It's when only one element is combined with a hydrogen. So, for example, HI is a hydroiodic acid, while HiO2 or HiO3 is iodic acid. So hydroiodic acid, hydro means there's only one element combined with it, but iodic acid means it's an oxyacid. Now, hydrates. Is this even on the exam? I really don't care though. Okay, well you get the gist of it. in the formula, it's, for example, MgCl2, and then there's a dot, and then there's a number, and then the water symbol. That just tells you how much, or the ratio of compound to water or whatever. I don't really care. It's not really on the exam. You don't need to know this. So, for example, MgCl2 dot 6H2O is magnesium chloride hexahydrate. Oh yeah, remember the mono ditri, tetra, penta, hexa, is it hepta? Nona, deca, octa. Wait, no, nona? I really don't care. Whatever. Yeah, you get it. Yeah, you got that. Good on you. Blah, 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 blah. Now, ionic compounds. I've already done this. Wait. Pause. Oh, I can't pause it. All right. Shortcut. All right, I'm back. Now we are on ionic, the Lewis dot diagrams for ionic compounds. Again, I really can't convey this over verbal stuff. This is just for me to study, but whatever. For this, you're gonna draw the symbols of each ion inside the compound. So, for example, is that even a thing? Okay, K3N. So we know that K has 1 electron and N has 5 electrons. No, N needs 3 electrons. I don't know why I'm saying N. Nitrogen needs 3 electrons. And since potassium only has 1 to give, we need 3 potassiums. So draw 3 potassiums, 3 Ks, with each having a dot, and then draw an arrow to the nitrogen where an empty space that a valence electron should be is. Point to that, and then boom, you've basically done that part. Then after that, you're going to have to show the ions at the end. So you're going to draw a bracket, and inside the bracket will be the symbol of one of the elements involved in the ionic compound. So for example, K, bracket, K, bracket, and then X outside, you're going to put the ionic charge of it, so 1 plus. But you're not done there, since you have 1 nitrogen and also 2 more potassiums to do. So nitrogen, you just put bracket N bracket 3 minus to indicate that nitrogen gained 3 electrons. And then you draw the other 2 potassiums and you are pretty much done. Now for covalent molecular diagrams, there's a whole lot of fancy stuff we gotta do. For starters, we're gonna do the S equals N minus A formula. I'm pretty sure you know what that is, but it means shared equals needs minus available. So S stands for the shared bonding electron that we need to know to draw the diagram. The N is the number of electron that each atom needs, and A is the number of electrons each atom has. So for example, let's do CH2O. S is equal to, since N, for N we have a carbon. Carbon needs 8 electrons. We have 2 hydrogens. Hydrogens only need 2 electrons, so we're going to do 2 times 2 electrons. And then oxygen needs 8 electrons, obviously, so we're going to add 8 electrons. That is N. And then minus symbol. And then for the A section, we have carbon. Carbon has 4 electrons, so we're going to put that in A. And then there's 2 hydrogens, but each only have 1 electron, so we're going to do 2 times 1 electron. And then at the end, since we have oxygen, oxygen has 6 electrons, we're going to add 6 electrons to the AA section. And that evaluates to 20 electrons minus 12 electrons, and therefore 8 electrons. But this is not the end. This means that 8 electrons are shared, and we have 4 bonding pairs. Now you can start to draw your diagram. What you're going to do is you're going to draw your symbols. Let's do C in the middle, H to the left, H at the bottom, O to the right. Now we're going to start drawing our bonding electrons. So 2 electrons are shared between hydrogen and carbon. Other 2 electrons are shared between another hydrogen and carbon. And since we have 4 more electrons or 2 more bonding pairs, we know that 4 electrons are shared between carbon and oxygen. So hydrogen is satisfied, other hydrogen is satisfied, carbon is satisfied, but oxygen doesn't seem satisfied until we realize that it has 4 non-bonding electrons. So we need to include the non-bonding electrons in the diagram. Just put 2 dots below and above. Yada, yada. And then you show the standard diagram, which is just that, but you replace the 2 dots representing electrons with dashes. So there's a dash going from carbon to hydrogen, there's another dash going from carbon to hydrogen, and then there's 2 dashes going from carbon to oxygen representing, well, the double bond. And now you need to do your bond or dipole thingies. You know what those are. You need to calculate the electronegativity of each relation in this ionic compound. So you need to calculate the electronegativity difference between carbon and hydrogen. I'll just skip to the point. It is equal to 0.37, and this means the bond is nonpolar, so the electrons are evenly dispersed, like mostly. And now carbon and oxygen, the difference is 0.99 in electronegativity, which means this is polar. So there is a slightly positive charge for carbon since it is the smaller one at 2.55, and there's a slightly negative charge at oxygen, which is the more attracted to electrons ones. It's at 3.44, and you would indicate this with a plus at the carbon and an arrow going from the plus to the oxygen. Or just use those silly little partial charge symbols that I don't really care about. Anyways, now we need to go to ionic and net ionic equations. Okay, can I even verbally convey this to you guys? Chat, should I do this? Water break. Excusez-moi. I'm just gonna leave this for myself. If you're listening, sorry. Yeah, let's just get straight to the point. Now, let's go to accuracy and measurement and blah, blah, blah. We're probably gonna not have to know this for the exam, but it's best to review, right? Estimated uncertainty refers to the limitations of the measuring device. It is half of the smallest division of measurement. So, for example, if a ruler can only measure by millimeters, then the estimated uncertainty is 0.5 millimeters. Relative uncertainty is a formula. It is estimated uncertainty divided by actual measurement times 100%. I don't think you're going to have to know this for the exam, but whatever. Percent error, you probably will have to know. It is the experimental value minus the known value, which you'll probably be given, divide by the known value, and then multiply by 100. Accuracy refers to how close a measurement is to a known value, and systematic errors account for accuracy. So, for example, bad calibration of devices, bad instructions in your lab, etc. And precision is the consistency of measurements. So, random errors account for precision. So, for example, human error, a bug like scares you or something. I don't know. Now, ionic bonding / compounds, whatever. Ionic compounds are between metals and nonmetals. Metals lose electrons, nonmetals gain electrons. It is quite convenient for the both of them. And ionic bonding is a transfer of electrons compared to the sharing of electrons of a covalent molecular compound, which we will learn about very soon. So the Lewis dot of an ionic compound, we've already done this before. You draw the symbol of the metal and the nonmetal. You show the transfer of electrons, then show their ionic charges at the end. Show the ions, yada, yada, yada. The chemical formula of an ionic compound tells us the ratio of ions in the crystal lattice. Cations and anions, which is the metals and the nonmetals ions, attract to form a crystal lattice, which is a 3D arrangement of millions of ions. Isn't that neat? Ionic bonds are simply just the electrostatic force of attraction holding oppositely charged ions together, so the cations and the anions. The properties of an ionic compound, It has a strong bond, high melting and boiling points. They are hard solids, not malleable or ductile. They are brittle because they break if force is applied. I don't know if you know this, but I remember if you hit them hard enough, it actually causes the crystal lattice to switch, because the rows in the crystal lattice alternate between positive and negative ions. So when you hit it hard enough, these rows will be clicked together with their positive charge rows will be connected with positive charge rows, and since they hate each other so much, they repulse from each other, and the whole thing just breaks. Well, most of it breaks anyways. And oh, my throat. And they also don't conduct electricity unless they are dissolved in water, because ionic compounds are electrolytes, and when their ions dissociate in water, they can conduct electricity for some reason that I'll probably explain later. Now, periodic table trends. So, periodic law states that if elements are listed by increasing atomic number, properties will recur in intervals, specifically intervals of 8. And we know this because of chemical families and stuff, but that's what the law states. The atomic radius is the distance from the nucleus to the valence shell. It decreases going from left to right and increases going from going down. Yeah, moving left to right, the nuclear charge increases, so electrons are pulled in more. Moving down, the nuclear charge increases, but more orbits are being added, so the atom is getting bigger, and the shielding effect kicks in. What is the shielding effect? The shielding effect is when the electrons in inner orbits reduce the nucleus's pull on outer electrons, meaning that, it isn't pulled as much, and the atomic radius is larger. The effect of nuclear charge, fun little tidbit by the way, I don't know if we have to know this for the exam, is the ability of the nucleus to attract and hold its electrons. Now, ionization energy is the energy required to remove an electron from a valence shell. It increases going from left to right and decreases going down. Moving right, the radius decreases and effective nuclear charges increases, which means stuff. And vice versa, moving down, radius goes up, effective nuclear charge goes down, yada yada. Electronegativity is the measure of the atom's ability to attract electrons. It increases going from left to right, decreases going down. It's the same thing as ionization energy. The radius decreases and the effective nuclear charge increases moving right, and vice versa moving down. And final, most important thing, electron affinity. The energy released when an electron is added, it's the exact same thing as ionization and electronegativity. Radius goes down and effective nuclear charge goes up, moving left to right, and vice versa, moving down. Main thing to understand, atomic radius is the only one that decreases going right and increases going down. Ionization energy, electronegativity, and electron affinity all increase going right and decrease going down. Now, fun stuff, covalent bonding and molecular compounds. This is between nonmetals only. Nonmetals have a strong attraction to electron and refuse to lose them. Instead, they choose to share electrons with their fellow nonmetals. A molecule is a group of atoms covalently bonded, so they're sharing electrons. Let's review covalent versus ionic properties. Ionic compounds are composed of ions in a crystal lattice. They are strongly attracted in a solid state. The chemical formula tells us how many atoms are in them. Oh, wait, never mind. That's a different thing. And for covalent compounds, they are composed of molecules in no particular arrangement, not a crystal lattice. And the molecules are somewhat attracted and can be any state of matter. The chemical formula of a covalent compound tells us how many or what atoms are in the molecule. It's not a ratio. L plus ratio. And a covalent bond is the region of overlap between valence orbits of atoms, specifically the nonmetal atoms where they share their electrons. There exist multiple types of covalent bonds. For example, single bond is when 2 electrons are shared between 2 atoms. So, for example, Cl-Cl, which is chlorine, and is also a Hofbrinkel element, so it bonds with itself and only exists naturally as Cl2. Double bond is O2, where two oxygens share 4 electrons between themselves to make themselves happy. And a triple bond, for example, is nitrogen N2, or just nitrogen, which is when nitrogens share 6 electrons between each other to make themselves happy. Diatomic molecules, elements that exist only as molecules in nature. Hofbrinkel, you know what it is. If you don't know, you're not me. Anyways, properties of covalent compounds continued. Particles are weakly attracted by intermolecular forces. I'm pretty sure you don't have to know the names, but it's specifically like London forces, blah, 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 whatever. They have low melting and boiling points. There's no ionic charge, and they cannot conduct electricity. Lewis dot of covalent molecular compounds was already reviewed. Now let's go on to polar stuff. So polar molecules are compounds with polar bonds, meaning there's a slightly positive end and a slightly negative end. Dipole forces are the attractive forces between molecules which are polar, meaning, how there are two molecules that both have positive and negative ends. Well, these oppositely charged ends will attract to each other. Nonpolar molecules are boring, they share it equally, whatever, yada yada, we don't care. A molecular dipole is when all of the dipoles shift in one direction in the molecule. And the octet rule, kind of random, doesn't really fit in with the rest of the stuff. It means elements bond to get 8 electrons in their valence shell. More polarity stuff. A bond is ionic when electrons are mostly with one atom or ion. So when the electronegativity is greater than 1.7. A bond is polar when the electrons are not equally shared, but it's also not fully decided. This is when the electronegativity is less than 1.7, but more than 0.4. And nonpolar is just when electrons are shared equally and they're boring, blah, blah, blah. Electronegativity is less than 0.4. All right, reaction time. I'll be back. And as fast as I left, I came back. Again, reaction stuff. Let's start with word equations. Word equations are when reactants and products are straight up just named. No symbols, no funny stuff. So, for example, iron plus oxygen equals iron 3 oxide. Different synthesis types. Normal, just element plus element equals compound. So, I don't even need to give an example. More important, metal oxide plus water is a metal hydroxide. Non-metal oxides plus water are oxyacids. We reviewed those. Those aren't really important, whatever. Decomposition types. Compound, normally it's just a compound turns into an element plus element. Metal nitrate decomposes into metal nitrite plus oxygen, and the rest does not matter. If a metal is more reactive than another metal, it replaces, you know the table for that stuff, the activity series of metals thing. You can use that to verify whether a reaction happens or not. Now, more importantly, neutralization reactions. Specific things you need to know: when an acid and a metal hydroxide combine and react, it produces water and a metal salt. So, for example, HA, which is the acid, and XOH, which is the metal hydroxide, produces HOH, or just H2O, which is water, and XA, which is the metal salt. And acid and a metal carbonate produce water, a metal salt, and carbon dioxide. So HA, which is the metal, and XCO2, which is the carbonate, produces H2O, XA, which is the metal salt, and CO2, which is the carbon dioxide. Now, combustion reactions. Combustion reactions are the reaction of a substance with oxygen producing an oxide and heat or light. A hydrocarbon is a compound of carbon and hydrogen. Wow, what a surprise. And complete combustion occurs when sufficient O2 oxygen is present, and incomplete combustion occurs when there is insufficient oxygen. So complete combustion produces water and carbon dioxide, and it has a high efficiency of heat. Incomplete combustion produces water, carbon dioxide, carbon monoxide, and just straight up carbon. A lot of carbon stuff. And it has a low efficiency of heat. Now, time for the more recent stuff. Moles. Molar mass is the mass of 1 mole of a substance. Using molar mass, we can now convert between moles and, who would guess, mass. Avogadro's constant is the number of particles in a mole. So 1 mole is equal to 6.02 multiplied by 10 to the exponent of 23 particles. Particles of an element. So particles is kind of a general term. For an element, it is atoms. For a diatomic element, it is molecules. For a covalent compound, it is molecules. And for an ionic compound, it's formula units. Why formula units? Who knows? Anyways, now we have a 3-way conversion. Number of particles converts to moles and vice versa, and moles converts to mass and vice versa. Now, a few laws. Law of constant composition states that a specific compound has the same composition anywhere in nature, even in space. And the law of multiple proportions states that when 2 elements can combine to form more than 1 compound, the mass ratio will be different because it's a different compound. Wow, who would have thought? Who makes these stupid laws? Okay, anyways, the molecular... Oh, wait, no, one more thing. When determining the mass percentage of an element in a compound without mass data, you can assume 1 mole and use molar mass to solve the stuff. Sometimes you also have to assume 100 grams of a compound too. A main thing, usually either you're assuming 1 mole or 100 grams. Yada yada. Molecular formula is the actual chemical formula of a compound and usually will be given to you later on. And an empirical formula is the simplest ratio of elements in a compound. For an empirical formula, all you need is moles A, colon moles B, colon moles C, etc. You know how moles are. Molecular formula is the molar mass of the molecular formula, the actual chemical formula, and the molar mass of the empirical formula. For the molecular formula, we need 3 things: the empirical formula, the actual molar mass, and the molar mass of the empirical formula. And once you get the result of the molecular formula, you're going to multiply each element in the empirical formula by the result of the molecular formula stuff. Oh, my head hurts. I have no water. Let's just finish this. Stoichiometry time. Stoichiometry. In a reaction, reactants and products are related by fixed mole ratio. So moles of substance A can be multiplied by Y moles of substance B over X moles of substance A to get moles of substance B. Sometimes there are limiting reactants. So for example, 2 moles of A produces 10 moles, but when it reacts with 8 moles of B, 8 moles of B only produces 8 moles of X. What does that mean? Well, the limiting reactant is the reactant that is fully consumed in the reaction. To determine the limiting reactant, I have made a 4-step process that you should probably follow. So step 1, convert all the provided masses into moles. Step 2, calculate the expected amount of product with each reactant. Step 3, the limiting reactant can be determined by the reactant that produces the least amount of product. Step 4, the amount of product produced will be produced by the limiting reactant because obviously it's the one that burns out first. To calculate the max of the excess reactant, the other reactant not fully consumed, you convert the limiting reactant into the excess and then calculate how much of the excess was used. Then the excess at the start minus the excess used should be what is left. All right, now stoichiometry percentage yield. Theoretical yield is the amount of product expected to be produced by stoichiometric calculation. And the actual yield is the actual measure of the product via an experiment or reaction. So these are two different things, kind of similar to molecular and empirical. Theoretical is what you calculate, actual is what happens. So percentage yield is the actual yield over the theoretical yield multiplied by 100%. Sometimes you'll get an impure mass data you can't use in the calculations. I suspect that he will include something along the lines of an impure mass data within one of these questions. So you must calculate the pure mass and then divide the pure mass over the impure mass, which is usually 100 grams, which will just straight up give you a percentage. Should be easy. Now, solutions. A solution is a homogeneous, which means a uniform composition, so it just looks the same no matter what angle or however you look at it. Homogeneous mixture of two or more substances. The solvent is the substance in a larger concentration, and the solute is the substance or substances in smaller concentration. So solvent is the large one, solute is the small one. Vent-ute. I don't know how to make an acronym for that or whatever. Ute-vent, vent-ute, whatever. Solubility is typically measured in grams per 100 milliliters, or more commonly grams per 1 liter. It is the measure of the max amount of solute that can be dissolved in a given amount of solvent, which is, again, usually 1 liter. A solution is saturated when it has the maximum amount of solute it can contain. It is unsaturated when it has less than the max amount, and it is supersaturated when it has more than the max. Supersaturated solutions are unstable and usually result in crystallization of some kind. Now, molar concentration. Molar concentration is the amount of solute dissolved in solution. So, amount of solute is in moles, and the solution is in liters. It is also known as molarity, and represented by the letter M. The formula for molar concentration, you know this, it's C, so molar concentration equals N moles divided by volume in liter. Concentration of ions in solutions. And this is important because he's probably going to send one of these questions your way. When ionic compounds dissolve, their ions dissociate. We know that because reasons. To calculate ion concentration, first calculate the molar concentration of the compound, and then convert it to ions with the mole ratio. So, for example, 0.176 moles per liter of iron 3 chloride can be converted to chlorine atoms through a conversion of how many moles of chlorine are in moles of iron 3 chlorine. So 0.176 mole per liter of FeCl multiplied by 3 moles of chlorine divided by 1 mole of FeCl3. You probably don't understand that, but I do. Anyways, sometimes you will do stoichiometry and molar concentration stuff together. Just do unit conversion stuff and just get to the point. Dilution equation. Don't use this a lot. Use it sparingly. Don't repeat your mistakes. Anyways, it is C1V1 equals C2V2. Kind of like physics. C1 is initial concentration, V1 is initial volume, C2 and V2 are new concentration and volume separately. Percent concentration, this is what kind of messed me up. Let's just hope he throws a softball for this one. You know the mass over mass percent. You have all the formulas. Just use them and hope it's not too hard. Now guesses. I'm going to take a break because my back hurts. I'll be back in like 1 second in this video. Alright, I'm back. Hang on. Okay, let's finish this. Gases. Pressure is the force exerted on an object per unit surface area. Pressure is equal to force divided by area. Atmospheric pressure, more importantly, is force exerted on Earth's surface by a column of air in a certain area. Different units of atmospheric pressure exist. For example, torr, kPa, psi, atm. For example, just convert between them. You know how. There exists specific sets of atmospheric conditions. STP, standard temperature and pressure. It is the freezing temperature of water and atmospheric pressure at sea level, and SATP, standard ambient temperature and pressure, which is more akin to room temperature and pressure conditions. Gases, properties, and behaviors. Screw you, I don't care. Anyways, ideal gas law. It relates volume, pressure, and temperature of a gas with the moles of the gas, using the universal gas constant, R. R is equal to 8.31 kPa multiplied by liters divided by kelvins multiplied by moles. Ideal gas law is PV, pressure volume, equals nRT, which is moles, universal gas constant, and temperature, or just N moles equals PV over RT. Units, volume in liters, pressure in kPa, temperature in Kelvin. To get Kelvin, you just get Celsius and then add 273.15, and then you get Kelvin. Stoichiometry with gases. You can use shortcuts. There are specific molar volumes at STP and SATP. You have them on your sheet, but for reference, it's 22.4 liters divided by 1 moles is molar volume at standard temperature and pressure, and 24.8 liters over 1 mole is molar volume at SATP. You will use your ideal gas law for stoichiometry with gases. Don't forget STP and SATP. Gas laws, Boyle's law is a fixed gas at constant temperature means the volume is inversely proportional with pressure. When volume goes down, pressure goes up, and vice versa. V1 P1 equals V2 P2. It is similar to the dilution equation. Use kPa and liters for volume and pressure units. Charles' law is fixed gas at constant pressure means the volume is proportional to the temperature. Temperature goes up, pressure goes up. Temperature goes down, pressure goes down. It is V1 over T1 equals V2 over T2. Use kelvins for temperature and liters for... Volumes. Okay. Use Kelvin for temperature, and the volume units doesn't really matter. Just make sure to use Kelvin. The Gay-Lussac law is fixed gas at constant volume. The pressure is proportional with temperature. Temperature goes up, pressure goes down. Pressure goes down, temperature goes up. Oh, for Charles' law, by the way, it's volume. Its volume goes up and temperature goes up, not whatever I wrote before. Anyways, Gay-Lussac is P1 over T1 equals P2 over T2. Kelvins for temperature, anything for pressure. I usually use kPa, though. And then there is I forget what law this is. I'm actually going to... It's the combined gas law. It relates all of the stuff before. P1 V1 over T1 is equal to P2 V2 over T2. Most important thing is keep the units the same on both sides and use kelvins for temperature. Avogadro's law is a gas at a constant temperature and pressure. The volume is proportional to the number of moles. As volume goes up, moles goes up. Wow, who could have thought? The formula is N1 over V1 equals N2 over V2. Molar volume is MV equals V over N, volume over moles. Molar volumes are again constant at STP and SATP. Last law for now, Dalton's law of partial pressures. Total pressure of a mixture of gases is the sum of the individual pressures of each gas within that mixture. So the P total, or PATM, is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, etc. Go on. And importantly, for collecting gas with water displacement, or if you're just trying to find the dry gas pressure, the pressure of the gas is equal to the pressure of the atmosphere, the pressure of the total, minus the pressure of the hydrogen at whatever temperature. You're going to have a sheet on your thing. It's going to relate to the partial pressure of water vapor at different temperatures. Just use that crud, whatever, yada yada. I think that's it for now. I'll add more stuff later if I need to, but I don't know. Anyways, make sure to like and subscribe so I can never do this again. Hope you enjoy.